forces acting at a distance involves the concept of a force field. Consider this planet in space. These orange lines represent gravitational field lines about the planet. Any mass in this gravitational force field experiences a force. Is the force acting on a satellite of mass m in the field? In previous lessons, we've described the gravitational force in such a satellite with Newton's law of gravity. An equivalent way is multiplying the mass of the satellite by the gravitational field of the planet, where the satellite is located. Then the force F on the satellite is its mass times the gravitational field, G. This is bold-faced G to distinguish it from the italic G we often use for acceleration due to gravity near Earth's surface. Both G's have units, newtons per kilogram. The field is stronger up close and weakens with the Earth per square of distance. The field plays an intermediate role between objects. Likewise, in electricity. Here's a proton surrounded by its electric field. The electric field is denoted by the symbol E. And here's an electron circling the proton. And what of the force on the electron? Much akin to gravity, the force equals its electric charge multiplied by the proton's electric field, QE. The magnitude of the electric field is simply the force per unit charge. If a charge Q experiences a force F at some point in space, then the electric field at that point is F divided by Q. When the force is expressed in newtons and the charge in coulombs, denoted by the capital letter C, the electric field has the unit Newton per coulomb, N over C. Both the fields for gravity and electricity are vector quantities, having direction as well as magnitude, and can be represented by vector arrows. The direction of Earth's gravitational field is toward Earth, inward, the direction of force on a mass in the field. The direction of the electric field about the proton is the direction of force on a positive charge in the field, outward. Since our charge is negative here, that of an electron, the force on it is opposite to the direction of the field. Here's a positive charge with a few of its field lines. They point radially outward. But what of the field lines about a pair of equal and opposite charges? We get this pattern, a pattern of curved lines. It's interesting to realize that the curved pattern is the composite of pairs of straight lines, outward from the positive charge and inward toward the negative charge. For example, consider the field at this point, where I place a green dot. A positive test charge here would feel a repelling force from the positive charge and an attractive force toward the negative charge. At this point, here's the force vector due to the positive charge. Here's the force vector showing attraction to the negative charge. We see it smaller in accord with the inverse square law. We draw a parallelogram for these two vectors, and this gives us the resultant force at this location, right here where the green dot is. Notice direction coincides with the direction of the composite field at this point. Let's do the same for this point. A force in a direction away from the positive charge, and a force of attraction toward the negative charge. And using the parallelogram rule, we get the resultant vector, and again, it aligns with the composite field at that point. We do the same for this point, and the parallelogram. And see that? Alignment with the field at this point. And for this point, same story. I could repeat this process with all the points in the electric field, and you know what? I'd get the curved pattern you see. A composite of resultant force vectors over an infinite number of points. A curved field that begins at the positive charge and ends at the negative charge. Is this young or what? Let's take a look at some photographs of electric field patterns. Here's a photograph of such field lines about a positive and negative terminal in a bath of oil. The field is shown by the orientation of bits of thread suspended in the oil. And not surprisingly, the field formed by the pair of equal and opposite charges is like the field I just sketched. We can use the same vector technique to show the field between a pair of positive terminals shown here. What's the resultant field halfway between the equal charges? Did you say 0? If so, yeah. Here's a photo of field lines between oppositely charged plates, called a capacitor. Notice the field is uniform between the plates, except near the edges. Why the field isn't uniform between the edges is something we won't get into in this lesson. But here's detail for a capacitor. Both plates have equal and opposite charges. And Cairo physics instructor Mona Nasser models a demonstration capacitor. Back to our field patterns. Very interesting is the field pattern for a plate and cylinder that have opposite charges. Notice the absence of a field inside the charged cylinder. All field lines cancel out. Why this is true is even more interesting, covered of course in your textbook. For now, we just want to say that inside any charged body, the field strength is 0. All field vectors cancel. Again, covered in conceptual physics. The fact that no field results inside a charged conductor is nicely employed in the Van de Graaff generator. Let's look at the operation of a Van de Graaff generator. We see that a voltage source leaks charge off metal points, in this case electrons. An insulating belt carries the electrons up inside an electrically insulated tube that supports the hollow dome above. Electrons leak off onto the metal point collectors at the top of their path and repel one another and gather on the outside of the metal sphere. No matter how much net charge accumulates on the outside of the dome, field strength inside is 0. That means charge can be added if introduced inside the dome without repelling away. Whereas any charge that approaches the outside of the charged dome is repelled away. Inside, not the case. The result is that charge can keep building up at the dome's outer surface until the build-up voltages produce electric discharge through the air. Then we have localized lightning bolts. Here we see Laurie Patterson touching a charged Van de Graaff generator. Note how her hair stands out. That's because it becomes electrically charged and strands of her hair are light enough to show the electric repulsion between the strands. The dome Laurie's touching is at thousands of volts. So why isn't she shocked, as should be, by handling a faulty 110-volt light socket? The answer has to do with energy. Voltage is energy per charge. Joules per coulomb. Only a tiny fraction of a coulomb makes up the charge on the generator dome. So a small amount of energy per tiny amount of charge can equal a huge voltage. So any energy transfer to Laurie is minuscule. But that's not the case with a faulty light socket. The flow of charge there is in coulombs, not tiny fractions of coulombs. The flow of energy can be fatal. When thinking voltage, think ratio of energy per charge. Are you getting this? I hope so. Let me leave you with a concluding question. Consider a pair of equally charged particles separated by a certain distance. If exactly midway between these particles, their combined electric fields cancel to 0, what can you say about the signs of charge of the particles? Are they like charges or unlike charges? Can you support your answer? Until next time, good energy.